Hello everyone, this talk is called MEGSim, a novel methodology for efficient simulation of graphics workloads in GPUs. This work was done by me, David Corbalán Navarro, and Juan Aragón from the University of Murcia, and Antonio González from the Universitat Politécnica de Catalunya. Well, as we all know, simulation tools and frameworks play an important role in computer architecture research. The purpose or the main goals of simulation is to model new ideas, estimate performance, measure power consumption, etc. Of course, a key factor of architectural simulations is the long time it takes. In particular, cycle-accurate simulations require a huge amount of time. In our case study, the simulation of graphics workload of, let's say, for example, 500 frames usually takes more than 1 day. And when hundreds of simulations have to be carried out, this becomes an important concern. In our work, we propose a novel methodology called MEGSim to achieve a more efficient simulation of graphic workloads. The idea behind MEGSim is to use clustering to group frames that exhibit a similar behavior. It is inspired by the underlying idea of SimPoint, which is a well-known approach aimed at general-purpose processors that cannot be directly applied to GPUs. With MEGSim, we were able to characterize graphics workloads by only using information from the graphics pipeline. Information that, as we are going to see, can be obtained by using a functional simulation. This led to an average reduction of 126 times in the number of frames to simulate, which means that the simulation time is reduced by 2 orders of magnitude, and at the same time getting a relative error lower than 1% for the different statistics that we have measured. To evaluate our proposal, we made use of TPOT, which is a toolset developed by the ARCO group from the UPC. TPOT allows to run Android applications and evaluate the performance and energy consumption of the GPU and the memory system. Regarding the target mobile GPU, we have chosen this one just as a proof of concept to evaluate MEGSim, since although it is a bit old, it is one of the most deployed Mali GPUs and still represents a good fraction of the mobile GPU market. Okay, on the other hand, concerning our set of benchmarks, we included both 2D and 3D games. The workloads are representative of the current landscape of smartphone games, as it includes popular Android games with millions of downloads according to Google Play. The evaluated video sequences with several thousands of frames have been carefully selected in order to get a representative use case scenario for each game. So, how is MEGSim able to characterize video sequences? The idea is to use the information about the execution of program shaders. A shader is a program designed to run on a particular stage of the graphics processors. We can distinguish between 2 types: vertex shaders that manipulate the input geometry and therefore determine the activity of the geometry stages, and the fragment shaders that calculate the output color of each fragment and determine the activity of the raster stages. MEGSim collects the number of times that each shader was executed in every frame. Afterwards, these values are multiplied by the number of instructions in each shader. Okay, but if only information about program shaders is used, we will be missing an important stage, the tiling engine. Therefore, for every frame, we also take into account the number of primitives. This slide shows pictures with the graphics pipeline of a mobile GPU implementing a TBR architecture. To sum up, as input parameters for every frame, we collect the number of times that each shader has been executed along with the number of primitives. A key factor of these parameters is that they can be obtained, as we previously said, by using a fast functional simulator. These simulators have much lower execution times compared to cycle-accurate simulators. These parameters can be combined to create a vector of characteristics for every frame. As you can see in this diagram, our vector of length d contains p elements that represents the number of times each vertex shader was executed, q elements with the count for the fragment shaders, and finally only one element with the number of primitives. In order to guarantee the parameters have an impact on the number of cycles, we decided to do a correlation study. The diagram on the left shows the results. It can be observed that the characterizing input parameters, especially the shader counts, have a high correlation with the total number of cycles. However, the number of primitives have a more limited impact on such metric. Therefore, since the impact is different, it could make sense to set a weight for each parameter. To do that, we measure the dissipated power in each of the three main phases of the graphics pipeline, just as a proxy of the activity performed on each pipeline's phase. The diagram on the right shows the results. Probably as expected, the raster stages are the ones with the higher power dissipation. The average values are used as weights for the three components of the vector of characteristics. Now that we have a vector for each frame, we can calculate how different two frames are by computing the Euclidean distance between their vectors. Two similar frames will have a distance close to 0. Then we can create a similarity matrix to find how frames relate to each other. In this example, you can see the similarity matrix for 900 frames of the benchmark PBR. The darker a point is, the more similar the two corresponding frames are. There are different patterns in this benchmark. For example, starting from point 200 and 200 and tracing a horizontal line, we can see a dark region until we reach the point 400 and 200. This means that all the frames between 200 and 400 are very similar. Now the idea is to group those frames that exhibit similar behavior. For this purpose, MEGSim uses k-means to produce a vector of length k with all the cluster's centroids, a vector of length n containing all the labels. This is the assignation of the frames to the corresponding cluster. And finally, the distances between the centroids and the frames. For each cluster, what we do is to select the frame with the lowest distance, and this will be the cluster representative. This is the frame that will be simulated. In this plot, we can see the 4 different clusters that have been drawn along the matrix diagonal. According to our technique, the idea would be to simulate only 4 frames out of 900. Each of those 4 frames will represent a different colored region. In order to determine if a set of clusters is a good fit for the data, MEGSim makes use of the Bayesian information criterion, or BIC, which is a penalized likelihood that measures the goodness of a fit. The algorithm that we have implemented is very simple. we just start with a single cluster and calculate the big score. Then we increase the number of clusters until a big score lower than the previous one is obtained. And the first clustering with a score that is at least 85% of the spread is selected. This 85% is a threshold that was empirically chosen and represents a trade-off between accuracy and the number of clusters. Now let's talk about the results that we have obtained. First, as mentioned before, we get an average reduction of 126 times in the number of frames to simulate, and this translates into an impressive reduction of more than 2 orders of magnitude in the simulation time. As we can see, the evaluated graphics workload can be properly characterized just by simulating an average of 33 frames out of almost 4,000 frames. On the other hand, and regarding the accuracy, here we can see how we were able to characterize the full simulation of a video sequence with a small subset of frames, also with a negligible error. For the sake of space, we focused our analysis on 4 key performance metrics: the total number of cycles, the number of accesses to main memory, the number of accesses to the L2 cache, and the number of accesses to the tile cache. The accuracy was calculated by comparing these output metrics when simulating the whole video sequence against the values we obtained when simulating the subset of representative frames. As we can see, although the higher complexity of 3D games slightly reduces the accuracy of the metrics, the average relative error is still lower than 1%. Apart from that, and in order to provide a better understanding of how well MEGSim behaves, we also implemented a naive technique based on random subsampling. This technique randomly selects the representative frames that characterize the whole sequence. To properly evaluate the accuracy of this random methodology, the tests have been repeated 1,000 times. And in the case of MEGSim, we repeated the tests 100 times and changing the initialization values of keymeans to obtain different results. In this table, we can see that in order to achieve the same accuracy as MEGSim, random subsampling needs to select, on average, 58.5 times more frames. We can also highlight the extraordinary results that MEGSim achieves in terms of accuracy, with a maximum relative error for the number of cycles lower than 1.5% and with a confidence of 95%. Finally, to sum up, this work introduces a novel methodology to efficiently simulate graphics workloads in GPUs called MEGSim. MEGSim automatically determines representative frames that are able to characterize a whole video sequence. And our experimental results showed that MEGSim achieves a remarkable reduction in the number of frames and with a negligible impact on the accuracy. So that concludes our presentation. We would like to thank everyone involved in this project. We hope that you found it interesting, and we would be very happy if this could contribute to your own work and research. We are going to continue improving this project to include new GPU architectures in our simulator and also in the MEGSim tool. Well, that's everything. Thank you very much for listening, and we look forward to seeing you at the conference.